Hi everyone, welcome back to the Bioinformatics Coach channel. In today's video, I am going to show you how you can call variant using the tool freebayes. For this tutorial, we are going to use a single sample. These are the activities we perform this exercise. We are first going to install the tools that we will need for this exercise. We will install FastQC, MultiQC, some tools, BWA, freebayes, BCF tools, and Tabix. We will use Anaconda to do that. We will then download the example data. We are going to use paired and FASTQ reads. We will also download the reference genome or reference sequence. After that, we will assess the quality of the reads. Quality control is important when dealing with sequence data, so you should always do that. We will then map the reads to the reference sequence. After mapping the reads, we will generate a BAM file which contains alignment records. We will filter the alignment records and select the relevant reads for the downstream analysis. We will then mark duplicates and remove them. Then we will perform the variant calling using freebayes. After variant calling has been done, a VCF file will be generated. We will perform some basic statistics on that VCF file, and then we will filter the variants. So these are the activities we will perform in this exercise. This tutorial was made using materials from the Galaxy platform. Okay, so let me take you to the page which has the original tutorial. Let's check it out. Okay, so this is the original tutorial, and I'm going to leave the link to this page in the description box. So the original tutorial here is what is titled Exome Sequencing Data Analysis for Diagnosing a Genetic Disease. So this is more like a bioinformatics project. Okay, for this tutorial, they use 3 samples, but I am using a single sample. I will make another tutorial where I show you how to perform variant calling when dealing with multiple samples. I will do that. And I also prepare another tutorial which will reproduce everything here. Okay, so that's what you need to know. For this tutorial, I'll cover these ones from step 2 up to step 6. Okay, that's the variant call. That's what I'll do. For the variant annotation and reporting, I'll do that in another tutorial. With Galaxy platform, for those who don't know, it allows you to run bioinformatics tasks using tools which have been installed on their server. But one thing about this platform is that it uses graphical user interface. So it's more like click, add, drag, drop. That's about it. So it's not a command line based. So what you need to also know that behind the scenes, commands are being executed to run the analysis for you. Okay. So Galaxy platform is good if you are starting to learn bioinformatics, but going forward, if you have lots of samples to analyze, it's recommended to use command line tools. So that is why I am reproducing this tutorial using command line tools, so that those who are beginners will get to be exposed. Okay, I will be exposed to how command line tools work. Okay, so that's why I'm doing that. So let's proceed. For those who want to learn more about the freebayes tool, the one we are going to use for the variant calling, you can find more information here. This is the page, the GitHub page of the developer. So just check that out. I will leave the link to this page in the description box. So take note of that. So let's proceed. Now, for those who also like to learn more, you can just send me a mail, and then we can also work out maybe a one-on-one session or group. That will also be cool. So that's about it. So if you want to read more, if you want to learn more about bioinformatics and you need extra coaching and advice, you can just contact me. So that's about it. Now let's get back to our tutorial. So for this tutorial, before you follow it, you need to make sure your PC satisfies some requirements. Let's look at the requirements. So here are the requirements. You need to have a PC which has at least 8 GB of RAM. If you have more than 8 GB of RAM, that's perfect. I would recommend a RAM higher than 8 GB, but if you have 8 GB, still manageable. For the number of cores, at least 8. Okay, so that's what you need to have. Better so if you have a computer server, a remote server, you can just use that to run the exercise. Okay, so this will allow you to run the task faster. For the software, you need to have Linux or macOS. These are operating systems. They are Unix-like operating systems. So make sure you use one of these. Linux is free, macOS is proprietary. So you need to decide which one is available for you. You also need to have Anaconda installed. We will use Anaconda to install the tools that we use for this exercise. Anaconda makes life easy when it comes to software installation. So just make sure you install it. For those who are new to Anaconda, I have tutorials that show how to install Anaconda. There is one tutorial that shows you how to install Anaconda on a Linux system. There's also another one that shows you how to install Anaconda on a macOS system. So these videos are available. The links to those videos are in the description. So just use them, set up your PC. Without further ado, let's start the exercise. We will go to the terminal and then continue. We are in the terminal now. And I assume that you have installed Anaconda. If you have not done that, make sure you install that. Links are in the description box. You can use those links to check out my videos on how to install Anaconda. So let's proceed. After installing Anaconda, what you have to do is to add channels. We are going to add 2 channels. So let me show you how. Say conda config add channels. We will add a first channel, which is bioconda. Let's add a second channel, conda config add channels. The second one is conda forge. Let's confirm that the channels have been added. So we say conda config show channels. So this will list the channels we added here. The default channel comes packaged with conda, so we will leave it as it is. So that's about it. We are now going to install the tools. So what we will do is to create an environment and install the tools that we will use them in that environment. So that's what we are going to do. So we say conda create -n. So let's name the environment variant calling. And then we install the tools. So we say fastqc, multiqc. We also have BWA, we have some tools, we have freebayes, we have BCF tools, and we have Tarix. So we will run this command and then conda will install the tools. So let's do that. Let's confirm by typing Y. Conda will download all the packages and then install them for us. So let's wait and see how it goes. Okay, so the tools have been installed. So let's proceed. From the statements here, conda tells us that if we want to use the tools, we need to activate that environment. So we will use this command to do that. So let's activate that environment. Let's clear the screen first, and then we will activate. So we say conda activate variant calling. Perfect. So now everything has been done. Let's do a quick test. Let's just run some tools. One of them, see. So some tools. Perfect. So it has been installed. And I assume that all the other tools have also been installed successfully. So that's about it. Let's proceed. We are now going to download the example data. We will download the FASTQ files and then the reference sequence. So let's do that. Let's go to the page where I showed the original tutorial. We will get the download links there. So let's go to that page. Okay, so on that page, just scroll down. There's an outline here. So let's go to this side here, get data. We will get there and then we will scroll down. We will see the data set. So these are data sets. For this tutorial, I'll use a single sample. So I'll use the first one, which is father. Because we are dealing with pair then reads, we will have read 1 and then read 2. So we will download all of them. To download, you can use your browser or you can use the command line. If you want to use your browser, just highlight that link, just right click it and then just open it. You can open it in a new tab as well. So once you open the link, you will be asked to save files. So we will do it one by one. So that's how you do it with the browser. But I will do everything on the terminal. So I'll just copy the link. I will start with the read 1. I'll copy it and then I'll move to the terminal to download it. So let's proceed. Okay, so on the terminal, I'll first create a working directory. This is a practice I always recommend. The reason why I want to create a directory is that I want to make sure all files that will be generated during this exercise will be separated from files that exist on my PC. This will prevent me from accidentally modifying files. So I will say make the variant colon and then I'll cd into it. So this is my main folder or my main directory. And then I'll say make the data. And I'll also say make the data slash /skill. Perfect. So that's what I have here. So the data directory, there's a subdirectory called /skill. This is where we will store the /skill reads. So now that we have this, let's download the read 1, the one and that's we copied its link. So we'll say wget. I'll use wget, but you can use any other downloader to also get the files. So that's it. So I'll say wget -p and I'll say data slash /skill. So -p here will tell wget that we want the data to be downloaded into this directory. Okay, so this prevents us from downloading it first and then moving. So we will do everything here. So I'll supply it with a link and then I'll run this command. So I'll do that now. The file has been downloaded. So if you do an ls data slash /skill, you'll find the file there. Now let's download it with 2. So let's go and get the download link. So I will copy the link and then I'll go to the terminal. On the terminal, I'll say wget -p data slash /skill and then I'll supply the link. Then I'll execute this command. Okay, so that file has also been downloaded. Let's check it out. Let's proceed. Let's do an ls data slash /skill and you will see the files there. So that's about it. Now let's download the reference sequence. Let's get a link. So on this page, just scroll down it, and then you see it there. So this is the reference, the reference sequence. We are using chromosome 8, HJ19. So I'll just use this link. Notice the .gz. This means that it has been compressed. Okay, it's compressed. So we will download and then we will decompress it. So let's go to the terminal and download it. On the terminal, I'll create another directory. So I'll say make the data slash ref. And I'll say wget -p data slash ref. And then I'll supply wget with a download link. So let's download this. Okay, so it has been downloaded. But because it's compressed, okay, we need to decompress this. We want the uncompressed file. We want the FASTA file. So let's first do an ls. So I'll say ls data slash ref. So this is it. So we want to decompress it and get the original file. So I'll say gen unzip data/ref/agent19. Yes, and then I'll execute this command. So this should do the job for us. So let's do an ls again, data/ref. You see the file there. So this is the first A file. Okay, this is the reference sequence, and we are going to use that later on. So now we have the data we need for this exercise. So let's proceed. We are now going to perform quality control. We will do this in order to assess the quality of the FASTQ reads. So let's go back to the Galaxy page and let's scroll up. Let's go to the steps here. Let's go to step 3, quality control. Let's click it and then get to that site. So here we will first run FastQC, and then we are going to aggregate the results using MultiQC. So MultiQC itself does not perform a quality control, but it aggregates reports that have been generated by FastQC into a single file, a single HTML file, and then we will read that HTML file using our browser. So that's what we are going to do. So let's go back to the terminal and then continue. Okay, so first of all, let's do an ls. We see that it's only the data directory that is available now, our working directory. So we are good to go. So let's proceed. So we are going to first run FastQC. So we will say FastQC, we say data/fastq slash star.fq.gz. So we want FastQC to assess the quality of all the files that end with .fq.gz. So we are looking at the FastQ files. So let's run this command. So FastQC is now running. Okay, so some analysis will be done and then reports will be generated. So let's wait for everything to be done. Okay, so FastQC has done its job. Let's check the reports out. So let's do an ls data/fastq, and you see some files here. So we have HTML files and then .zip files. So the files that we have, okay, their respective reports have been generated. So we have them here. So what we are going to do is to aggregate all the reports together. Okay, that is what MultiQC does. And this approach is useful, especially if you are dealing with lots of samples. It aggregates everything into a single file. You can just read that file and then select the samples that you want to inspect. So that's about it. So we will run MultiQC now. So we will say MultiQC, and then we say data/fastq/star, and then we indicate the extension. So we say star_fastqc.zip. Okay, because that is the file that FastQC generates. So this here, all the files that FastQC have generated, the zip ones, MultiQC will read them and then aggregates the reports together. So let's run this command. Okay, so MultiQC has also done its job and all the reports have been aggregated. So if you look at the logs here, it says what? Found 2 reports. So these reports have been aggregated. So let's do an ls, and then you see this HTML file here. So this is what MultiQC generates. So this has the report for the 2 outputs that FastQC generated. So let's look at this report. We will look at it using our browser. So let's check it out. Okay, so we have our reports ready. These were generated by MultiQC. Before we open the MultiQC report, let's look at the individual files that were generated by FastQC. So we will go to data and then we will go to FastQ. So let's open that. So you will see an HTML file and a zip file for each FastQ file here. So if we had specified 10 files, then each of the 10 files will have a report generated for it. So take note of that. Now let's look at the report for read 1. So let's open it. We will use our browser. So I'll double click and then my browser will open it for me. Okay, so we have our summary here. What you should know is that for every FastQC report, each summary will have one of 3 colors. So we can have a summary with this color, which is green. We can also have this, and also have this. If it's this color, that means everything is okay. If it's assigned this color, that means there's something probably wrong, so you have to check. It's a warning sign. If it's this color, that means something is really, really wrong. That's what you need to understand here. For this tutorial, I will focus on the per base sequence quality. That is what I will focus on. I will make another tutorial where I go into details with QC. So that's about it. So if you look at the per base sequence quality, you will see that they are all in this region. Again, we have our 3 colors here, this. If it's here, that means quality is very low. That means poor quality. If it's here, somehow. But if it's in this area, that means high scores, indicating good quality. And as we can see from here, all the base scores, all the scores, okay, the per base sequence quality scores, they are all, almost all of them are in this region. So that means the reads are okay, reads are good. That's about it. But you can also see some of them are moving towards this side, which is normal for paired and reads. You always have at the end, okay, having low quality. The quality reduces as you go to the end of the reads. So that's why you see this. So if you have some reads, most of the time you will see that as it goes towards the end of that read, you see it's dipping. The scores will be low. That's about it. Let's check the read 2. Okay, so let's look at read 2. Let's open this. And then we have that also here. Read 2, we also have a similar observation when it comes to the per base sequence quality. So it's also good. But then if you are dealing with lots of samples, then it's going to be very cumbersome trying to read each of these HTML files. And this is where MultiQC comes in. MultiQC will aggregate all the reports into a single HTML file for you. So that makes it easy for you to do your comparison as well, and then inspection. So let's open the MultiQC reports. So let's go to our main directory, which is variant colon, and then let's open this report. Okay, so we have that here. So it's the reports here that have been aggregated here. So that's what you need to know. So you have the mean quality scores here in this region, meaning everything is okay. Have this also here, everything is okay. So let's go to the Galaxy page and then look at some statements here. So it says that what the sequence quality is quite good overall. If anything, you may have to trim the 3' ends of the reads. Okay, I made mention that towards the end of the reads, the quality declines. So that is why the Galaxy authors also recommend that you trim the 3' ends, but we will leave it as it is, okay, because the reads in general are good. Their quality is high, the scores are high, so we are dealing with quality reads. So we will leave them as they are. There's one thing we need to observe. So that is point 2. Let's look at it. This statement is very important. In whole genome sequencing, a non-normal distribution of the GC content of the reads from a sample is typically considered to be a hint at possible contamination. Okay. But here we are dealing with sequencing data from captured exomes. That is reads that are not representing random sequences from a genome, but rather a bias selection. So we are not using whole genome sequence, but we are using exomes. And this means that we are going to have a non-normal distribution of the GC content. That is what this means. So we have what a bimodal GC content distribution. Okay, that's what it's giving us here. So this indicates that what we are dealing with exome sequencing data, or we are dealing with exome sequence. That is what it means. So when you see a bimodal GC content distribution, it's a characteristic of exome sequence data. That's what basically this means. So let's check the QC reports again. We just want to look at what this document is referring to when it comes to the GC content distribution. So let's just look at the FastQC one, for example. This is what's talking about, where we have the red color. So that's the GC content. So this where we have this red color. So this red color, I made mention that it tells us that something is wrong. Okay, and here the color shows something is wrong, but this is because we are dealing with whole exome sequence data. That's what it means. We are dealing with exome data. Let me put it that way. We are dealing with exome sequence data, but FastQC probably is assuming that we are dealing with whole genome sequence data. That is why we have this color showing, indicating there's something wrong. But in reality, there's nothing wrong. That is what this statement is explaining to us, that we are going to see a non-normal distribution of the GC contents. Okay, we are seeing a bimodal distribution. Okay, that is why FastQC is giving us this color here, telling us something, but there's nothing really wrong, just because FastQC is not able to identify that we are dealing with exome sequence data. It's giving us this color. When we check the multi-QC report, let's look at the GC contents here. We will have a similar thing. There will also be that red color. So that's what we have. So that's about it. So let's proceed. Let's go back to the Galaxy tutorial and then look at the next activity. The next thing we will do is map the reads to the reference sequence. That is what we have here. So we are going to use BWA. And we will use the BWMM command to do that. So let's go to the terminal and continue from there. Okay, we are now going to perform genome mapping. But before we perform genome mapping, we also need to index the reference genome. So let's look at how we will do that. Let's clear the screen first. Let's check our reference genome. This is our reference genome. We are going to map the reads to this reference genome. And as part of the mapping activity, we will need to index this reference genome. So let's do the indexing first. So we say BWA index. We say data/ref/AJ19. This one here. So let's do that. So indexing has been done. Okay, we have the indexing done. So we'll proceed. So if you do an ls into the ref directory again, you will see that some files have been generated. So let's say ls data/ref. You see that other files have been generated. So we need to have these there. Now we will perform the mapping. So let's proceed. Before we perform the mapping, let's look at the data again. So ls data pascal /star.gz. star.fq.gz. We just want to highlight only the FASTQ files. So we have them there. There's something I want you to take a look at. Look at the file names here. You see what we have here. You also see this. So in my opinion, these are long file names. Okay, so what we will do is to assign these names to variables so that we will have the names shortened for us. So we will do that. We're also going to do the same for the reference genome. So let's say ls data/ref. We will do the same for this one as well. So let's do those ones first. So first of all, I'll say ref equals data/ref/hj19 chr8.fa. I will do this one first. And I will do the same for read1, read2. So read1 equals to read1 will be equals to data/fastkill/father r1.fkill.gz. So let's do that. And then read2 equals to data/fastkill/father r2.fkill.gz. So we have them done. So we are ready to go. Now, aside these ones, we also need to make sure we add read groups. Read groups are important. So the read groups, we will include the sample ID and then the sample name. Let's go back to the Galaxy page and I will show you what I'm talking about. This is the Galaxy page. So yeah, it says that we should set read groups. That is what it means. So we are going to use the information here. So this will be the ID, the sample ID, and this will be the sample name. We need to add that. So we will proceed with that. It's important to do that because some of the variant callers require you to add read groups to your BAM file, the BAM file that you generate. Okay, so it's important to do that. So in the process of mapping, we set the read groups and then BWA will just add them. So let's proceed. Let's go back to the terminal. Okay, so let's set the read group. We will need to create some variables here as well. So the first one will be the sample ID. So I'll say origin ID. That's for the sample. I'll say origin ID equals 000. And I'll say origin SN. That's for sample name. I'll say father. And now we are going to set the read group itself. So let's look at the script here that I prepared. So I am going to set the read group using this one here, this particular text here. So I'll just copy this. This is the script for this tutorial. And if you want to download the scripts, you can check the description box. I'll leave the download link there for you to get it. So that's it. So I'll just copy this. This is what I'll use. I'll explain something here. So I'll copy this there. I'll leave this text also in the description box. So you don't need to type everything. Just go to the description box and you'll see this there. So just copy everything there. Let's go back to the terminal. So on the terminal, I will say read group equals, and then I'll paste this there. So here, there's what I want us to discuss. This dollar and then the origin ID in curly brackets is telling bash that we want the actual value. You know, origin ID is a variable. That's what we had here. So what we have here is the actual value, which is 000. That will be placed here. And then the RGSN, that's sample name, that will also be here. So this here is what this one here. So that is what we have here. So we've set it. We've not started the mapping yet. We are only defining the values that we will use when we are finally setting the read group. So that is what we have here. So let's run this command. Okay, so that has also been done. So we'll proceed. So now if you do an echo $read group, this is what you see. You have everything there. So this thing here is what we will use. So that is what the read group. Okay, so we'll proceed. The last thing we will do before mapping the reads is to create a directory. This directory will be used to store the output files. So we'll say make the, it should be in lowercase, make the bums. We are going to generate one BAM file, but we will process the BAM file and then generate additional BAM files. So that is why I am using the name BAMs. I have that done. Now we are ready to map the reads. So I say bwa mem-t and then I say 8. This is threads. If you have more CPU cores, you can increase this. You increase this, BWA will run faster, but I am using 8. I'll now say -r and I'll say quotes $read group. Then I'll add my second double quotes. I'll now say $ref. I'll say $read1, $read2. So that's what I have here. This entire line here, this particular quotes here, these quotes, okay, the command here will generate alignment records. And so we need to also specify an output file. Okay, so what we are going to do is that we are going to add an additional command which will save everything as a BAM file. So I will just add my pipe command and then I'll say samtools view -h-b and I'll say -o for output. I'll say bams/father.raw.bam. I'll use this. Let me also say that the strategy we are using here is useful, especially if you are running lots of samples. So if you're running lots of samples, then along the way, you can just assign the file names to the variables here and then use that here. Okay, so that's what we have. Now, if you are dealing with lots of samples and you are having a challenge, you can still contact me and then we can just arrange and then resolve that issue. So just make sure you do that. Now let's proceed. I have my final command, so I'll execute this and then generate the BAM file. Okay, so let's wait for BWA to map the reads. Okay, read mapping has been done. So let's proceed. So let's do an ls into the BAMs directory. And then we will see this there. So this is the BAM file. This is the raw BAM file. So that's what we have here. I named it raw because we will process this BAM file to generate our final BAM file. So that's it. Now, after read mapping, it's advisable to check the statistics, okay, the mapping statistics. So let's do that. So you say some tools flag stats, and then that is just one T. So flag stats, and then we say BAM/. father.raw.bam. So this will give us some mapping statistics. So let's run this. Perfect. So it will tell us the percentage of reads that's mapped to the reference sequence. Okay, so that's what I have here. I'll just focus on this one here, the one that's mapped. So we have majority of the reads mapping to the reference sequence, which is good. Okay, so this statistics will help you, okay, to kind of understand what has happened in terms of the number of reads that's mapped. And ideally, we should have majority of the reads mapping to the reference. This will let us know that indeed we are dealing with the right organism. So that is something you have to also look at. So if, let's say, you are dealing with human genomes, you perform your read mapping and realize that most of the reads, or quite a substantial number of the reads, are not mapping to the reference sequence, then you should investigate further. That means probably something is wrong. It could be contamination, it could be sequencing error, etc. But you just need to make sure you check that as well. So that's about it. Now let's proceed. We have our BAM file generated. What we are going to do next is to filter the alignment records. I made mention of that. Now let's go back to the Galaxy page. I am following the tutorial, so I am trying to make sure I reproduce everything that has been stated in that particular tutorial. So let's go back and check the next step. So if you scroll down, it says mapped reads post-processing. So let's look at it. So for the post-processing, we have some description here, but I'll skip that. I'll come to this one here because that is what is of interest to us. So we will filter the mapped reads. So here, what we are going to do is that we are going to filter using the flags. Okay, I'll give an example here. What we are going to do is that we are going to remove reads that are not mapped to the reference sequence, and we are also going to remove reads which have their mates unmapped to the reference sequence. So that is what we are going to do now. So let's proceed. So let's clear the screen first and then filter the reads. So we will say sum tools view -b-f. The -f, the F here is uppercase because we are using that to exclude some reads. So you say 0xc. This is hexadecimal. Okay, this is used to exclude reads that's the non-map, and also reads with mate pairs that are non-map to the reference sequence. So that is what we are doing here. We specify the BAM file, which is bams/father.raw.bam. Then we specify an output. So we say -o. We say bams/father.filtered.bam. Notice how I use the same sample name, but then the extensions here are different. So the extensions are used to differentiate the outputs, okay, for the different steps. So that is what I have here. So I'll run this to filter the reads. Okay, so we have done the filtering. So let's do an ls into the BAM directory, and we will see that file there, the new one we generated here. So we are ready to go. We are now going to mark duplicates. Again, let's go to the Galaxy page and see what has been written there. Okay, so we have that here. So on the Galaxy page, we have remove duplicates. Okay, so that's what we have here. So with this documentation, it's used as some tools command called rmdup, but this particular tool is now obsolete. And so what some tools tells us is that we have to use the mark duplicates tool. That is what we have. So I'm going to use that mark duplicates to mark the duplicates and also remove them. So let's proceed. Let's go back to the terminal. Okay. Now, to remove the duplicates, we need to follow some steps. So we need to first sort the BAM file by name, and then we need to apply fixed mate, and then we also need to sort by coordinates, and then we finally mark and remove the duplicate. So let's start. We will first sort by name. So we say sum tools sorts our specified threads to be 8, and I'll say -n. That means we are sorting by name, and I'll specify the BAM file. So we say bam/father.filter.bam. Say -o bam/what father.sorted.n.bam. Yeah, I'm using .sorted.n.bam so that I know that this BAM file was sorted by name. So I'll run this command. The BAM file has been sorted. We are now going to apply fixed mates. So we say sum tools fixed mates -m, and we say bam/father.sorted.n.bam. Then we say bam/father.fix.bam. So this is the output file for this step. So let's run this command. Okay, that step has also been completed. Now we are going to sort the BAM file that was generated here, this one here. We are going to sort by coordinates. So we say sum tools sorts, specify the number of threads, use 8, say bams/father.fixmate.bam. We specify the output, so we say bams/father.sorted.p.bam. So we are sorting by coordinates, so I'll use this name. So let's run this. Perfect. The sorting has been done. We are now going to mark and then remove the duplicates. So we say sum tools mark dup. We say -r. So -r here means that we are marking the duplicates and we remove them. Say -at. Specify the number of threads. Let's use 8. Say bams/father.sorted.p. And we specify the output file. So we say bams/father.dedup.bam. So this is the final BAM file. This is what we are going to use. So let's run this command to get that file. Perfect. So that has been done. So we are now ready to roll. We have marked and removed the duplicates. So we have what you call the BAM ready file. So we are ready to go. We are now going to perform the variant calling. Okay, so we have removed the duplicates. So this is the file that we are going to use, the final BAM file. So we call it the BAM ready file. What we are going to do next is to index this BAM file. So we will say sum tools index and we specify that BAM file. So we say father.dedup.bam. So we are going to index this. Now we have it done. So if you do an ls into bams, you will find that the dupe one has another file called .bai. So this indicates that we have indexed this BAM file. So the BAM file is now ready for the downstream analysis. So that means we can now call the variant from this BAM file. That is what it means. If you don't index, then some of the programs may not work. Some programs, let me just put it the way, some programs require you to have BAM file, which is indexed. And that is why we have to index this. And freebayes also requires us to index the BAM file. That is why I had to do that. So now we are ready to call the variant. So let's proceed. Let's go back to the Galaxy page and see what is there. Okay, so we are there. So there is a short statement here that you can read to get extra information. With the Galaxy tutorial, they use multiple samples, but I am using a single sample. So the procedure here has been changed a bit, okay, to suit what I'm doing. So that's it. Again, I'll make another tutorial where I demonstrate how you can call variants when dealing with multiple samples. So make sure you come back to this channel to watch that. Oh, and before we go to the terminal, let me repeat again that you can find the manual for freebayes here. It is the GitHub page, so just make sure you check this link and then get some useful information here. So let's go back. We will go back to the terminal now. Okay, so on the terminal, we will perform the variant call using freebayes. But before we do that, let's create a directory called VCF. Let's say make the VCF. So let's create this directory. We will use this directory to store the output file that we will generate after variants have been called. So let's go. Let's clear the screen first. We are now going to call the variants. So we say freebayes, and we say -f. -f here indicates the reference genome. So I'll say data/ref/aj19 underscore chr8.fa. And I'll say -b to indicate the BAM file. So it's bams/father.dedupe.bam. We say -vcf. So this tells freebayes that we want to generate a VCF. We want the output file to be in the VCF format. So we say VCF / father VCF. That's what we have here. So this is the full command. So let's run this to call the variants. Okay. The variant calling has been done successfully. So if you do an ls into the VCF directory, you will see that a file has been generated. Let's look at that. Perfect. So this is the VCF file. What we are going to do next is to compress this VCF file. So we will use the bgzip command. So we say bgzip, we say VCF / father.vcf. Perfect. So it has been done. So we have compressed it. The reason why we are compressing is that we are going to process this VCF further. We are going to manipulate it using BCF tools. And some of the commands that we use in BCF tools require that we have a bgzip file. So that is why we are compressing it into this format. So that's about it. So now let's proceed. Let's clear the screen first. we are now going to index the VCF file. So we say VCF tools index. We say VCF slash father.vcf.gz. So we are going to index it. Perfect. We are indexing because some of the commands in VCF tools require us to use an indexed VCF file. So we are done with that processing. Now we are going to perform some basic statistics. We can count the number of variants identified. So to do that, we can say zgrep-v-c. Then in quotes, we give our caret symbol and hash. And then we specify the VCF file, which is VCF slash father.vcf.gz. So we have that here. So this one, what we are doing is that we are counting all lines that do not begin with hash. Okay, so those are the variants. That's what we are doing here. So let's count this. Perfect. So we have this here. So this is the number of variants in that VCF file. Let's count the number of snips and then indels. So we can say BCF tools view -v, and then we specify the VCF file. Before we specify, we need to give the type. So -v here is used to specify the type of variants. So let's say snips. Then we specify the VCF file. Now we issue our pipe and we say grep-v-c. Then we bring this expression again. So this will count the number of snips for us. Perfect. So this is the number of snips. This whole expression here, we can assign it to a variable. So we can even say number of snips equals $. We say BCF tools view-v snips VCF slash father like this, and then we say grep-v-c. We bring our expression here and we close it. So now we can say echo $number of snips. That will give us that number there. We can also count the number of indels. So we say BCF tools view-v. Here we specify indels. Say VCF slash father.vcf.gz, and then have our grep-v-c like this. And we can get a number of indels. So we have that here. So it says what, 603. So the number of variants that are indels are 603. So these are things you can do. And I have a separate playlist that shows how you can handle and manipulate VCF files using BCF2. So you can just check that out. I'll leave the link to that playlist in the description box. So that's about it. So there are lots of things you can do here once we generate the VCF file, but we will do more later on. Now we are left with the last activity, and that is filtering the VCF. After generating the VCF file, it's important to filter and then get the high quality variants. Then you can use that for your downstream analysis. So I will show you how to do some filtering here. Of course, we've already started the filtering. The view command allows you to view certain variants. So for example, this view command we had here, we can use that to select only snips or only indels. So let's do that. So let's filter out and let's say we want only the snips. So we can say BCF tools view-v snips. We specify our VCF file. We say -oz. That means the output format should be what? GZIP. we say -o, and then we specify the output file. So we will say vcf slash snaps.vcf.gz, and then we run it. So now we will have the file created, and then the variant of the type snips will be in that file. So let's look at the file. It's in the VCF directory, so we can say ls vcf. See that file there. That is the one here. And so here we can still count the number of variants in that file. So we say zgrep -v-c. We indicate our expression. We specify the file, which is vcf slash snip.vcf.gz. So we have the number there. So the number we have, which is here, will be the same as what we did here. So that's how it is. So that's it. Aside filtering using the variant type, you can also filter using other criteria such as quality, such as chromosome position, chromosome number, etc. So we are going to look at a few examples here. So to filter, there is a command that can be used to do filter. That command allows you to specify expression. So to filter a VCF, we use BCF tools filter. Then we can give our expression. But before we continue, let's go to the BCF tools page and look at how the BCF tools filter command is used. So this is the BCF tools filter page. So here we have a number of stuffs here. So for this tutorial, we will just use this flag here, the include expression. We will just look at 1 or 2 commands, and that'll be it. So that's what we will do. So it allows you to specify some expressions that can be used to filter out. So let's look at some of the expressions here. So we have some expressions here. So you can just read more and then look at the examples here. Okay, so yeah, so we have that here. So let's go and then just issue 1 or 2 commands to filter. So let's do that. Okay, so we are here now. So what we are going to do is to filter and select variants that have a quality score greater or equals to 30. So we will do that here. So we will say VCF tools filter. We say -i, and we give our quotes. We say qual greater or equals to 30. So this becomes our expression. Then we say VCF further like this, and we say -o z, then -o. We say VCF variants. Let's say, let's just use this word. Let's say quality. Or let's just use a different one. So let's say variants.filtered.vcf.gz. That's it. So we can run this command now. Perfect. So now we can just grep into it. So we can say zgrep -v-c, and we say what? We give this one here, and we say VCF variant.filter.gz, and we can see that here. So you can see that this is the number of variants with quality greater or equals to 30. So this is a way to also filter out if you want to be stringent. Okay, so these are things you can do. So in a nutshell, there are lots of things you can do after you have called a variant and you have your VCF file. And the activities you can do will also depend on the number of samples you have. So if it's a single sample, there are things you can do. If you have multiple samples, there are stuff you can do. So you always have to read papers, look at the best practices, and look at examples, and that will help you to analyze your data. So I am going to prepare another tutorial which shows you how to call variants when dealing with multiple samples, and I'll still use freebayes as well. So that's about it. I've already covered some tutorials on how to use BCF tools to also call variant and how to use Snippy. And I'll also prepare some other tutorials, and we are going to use GATK. We're also going to use VASCAN. So there are lots of things that I'll be doing. So just make sure you come back to this channel to watch. So that'll be all for this tutorial. If you also have some comments, just leave them in the comment section. Let's discuss something new. So thanks for watching, and I'll see you in the next session. Goodbye.